Hello guys, we are back with our next tutorial. In this tutorial, let us go through dynamic hashing. So in the last tutorial, we have gone through static hashing. So we have discussed that the drawback of static hashing is that there will be a limited outputs. So for there are many functions for which we will be getting limited outputs. So the memory locations may repeat and which causes collision. Fine. Okay, so now in this tutorial, let us go through dynamic hashing. So dynamic hashing will expand dynamically, guys. It may shrink or it may expand dynamically. So the drawback of static hashing is that it does not expand or shrink dynamically as the size of database grows or shrinks. Shrinks is nothing but decreases. Okay. So in dynamic hashing, data buckets grow or shrink, added or removed dynamically. So hashing is done dynamically. So when we remove or when we insert, the size of the record, so the size of the table will be increasing or decreasing according to the insertions which we do. So dynamic hashing is also called as extended hashing. So now let us go to the definition of extended hashing. So it is a dynamic hashing method. So it is a method, guys. It is not also called, it is a method. Okay, so method where in directory and buckets are used to hash the data. So here we'll be using directories and buckets. So previously we used hash function, right? So here we'll be not using anything like that. We'll be using directories and buckets are used for hash the data. So it is an aggressively flexible method. So here there is a very less chance of collision. As we can say, even there will be minute chances of collision. So if order is 3 is given, once we reach 4, we'll be just splitting it again. So the collision chance will be reduced really less, but if it is a very large database, it might be complex using these things. Fine. Okay, so now let us go to directories. So the directories store the addresses of the buckets in pointer. So each bucket will be having an address, right? So those addresses will be stored in these directories, and the IDs are assigned to each directory, which may change each time when the directory expands. So if it is expanding, it's having some submodules, right? Or if it gets compressed, it will be reducing its submodules. So in that way, we will be changing the addresses. So bucket. So the buckets are used to hash the actual data. So actual hashing is done in buckets. Fine. Okay. So here they gave a small problem to. So they told us to do extendable hashing for the given keys. Okay. So the first step for this extendable hashing is that you need to have an idea on how we will be writing the binary codes, guys. I hope everyone has a small idea at least how we will be writing these binary codes. So I'll be explaining you again. Don't worry. Okay. So just give me a second. I'm taking a piece of paper. Okay. So binary code. Binary. The number binary indicates that the number which you should represent the number in terms of zeros and ones. Binary means 2 zeros and ones. Fine. Okay. So in the question they give 60, 16, 4, 16, 6, 22, 60, 24 like that, right? So you'll be doing in this way, guys. I will follow this method basically. Okay. So from right side, write 2 power 0, 2 power 1, 2 power 2, 2 power 3, 2 power 4, 2 power 5. Fine. So here we may not reach up to 2 power 5 also. Okay. So this is 2 power 0 is 1, 2 power 2 is 2, 2 power 2 4, 2 power 3 8, 2 power 4 16. Fine. So our first value is 16. So by adding what you'll be getting 16, guys, you need a single 16 and all zeros. So this is nothing but 16. For 4, you need a single. We'll be doing it dynamically, right? All the values which are given to be hashed, guys. Okay. So these are all the binary codes for the given question. 16, 4, 6, 22, 24, 10, 31, 7, 9, 20, and 26. Fine. So once we are starting hashing, so I told you, we'll be doing it dynamically, right? So initially, the only binary combinations which we will be considering as 0 and 1. So even this whole process you can do in single step, guys. But let us assume it step by step so that it will be clear for you. So initially we'll be inserting initially let us assume the position of the particular thing right at this moment. 0, 1. So here we'll be storing the values of 0, here we'll be storing the values of 1. So this is the first combination. There are no combinations yet. Okay, 1. So this is the initial stage of this. So once we are inserting 16, so we'll be considering the last bit, guys. Last bit. So here the combination is only single letter, single code. So we'll be considering only single code 0. So we will be inserting it in this column. So you need to write again. You write insert 16, and you just write in this. So insert 16 after that you write like this 1, 2, 3, 4. Underline the 16. So due to that you're drawing like that. So we can understand. The evaluators can understand 16. Here, fine. So further moving on, we need to insert 4. 4 is I'll just update here only, guys, so that we can have a clear idea. 4. So what is the code of 4? It is 0, 0, 1, 0, 0. So again the last code is 0. So we'll be inserting 4. And remember the order will be given in the question. So it's here, guys. I think it's hidden. Order is 3. So once we reach 4, we need to overflow and we need to split it. So we reach 4. So after that 6. 6 is the combination of 0, 0, 1, 1, 0 again 0. So we substitute 6. And when we consider the next thing, it is 22, 1, 0, 1, 1, 0. Here also we reached 4, guys. So here we are having 4 things, but our order is 3. So now let us split this to 0. So if we split 0, we can write it in. So once we reach 4, we need to overflow and we need to split it. So we reach 4. So after that 6. 6 is the combination of 0, 0, 1, 1, 0 again 0. So we substitute 6. And when we consider the next thing, it is 22, 1, 0, 1, 1, 0. Here also we reached 4, guys. So here we are having 4 things, but our order is 3. So now let us split this to 0. So if we split 0, we can write it in two combinations, right? Okay, so 1, 2, 3. So 0, 0, 0, 1, 1, 0, 1, 1. Fine. Okay, so 4. So after that 6. 6 is the combination of 0, 0, 1, 1, 0 again 0. So we substitute 6. And when we consider the next thing, it is 22, 1, 0, 1, 1, 0. Here also we reached 4, guys. So here we are having 4 things, but our order is 3. So now let us split this to 0. So if we split 0, we can write it in two combinations, right? Okay, so 1, 2, 3. So 0, 0, 0, 1, 1, 0, 1, 1. Fine. Okay, so till now we did not open the account of 1, right? So there are no entries in it. So we can combine these two as empty. Instead of drawing 2, we'll be drawing in this way. Whereas the 0, 0 combinations, please write these again. So this is a 0, 0 combination. That is nothing but 16. 16 is a 0, 0 combination. And the next value, that is 4. 4 is also a 0, 0 combinations. Similarly, 1, 0 combination. So this is 1, 0, this is 1, 0. Those two are nothing but 6 and 22. So 6 and 22 will be stored in the 1, 0 combinations. So further moving on, we got 24 with double 0 combination. So we'll substitute it here. Further moving on, we got 10 with 1, 0 combination. We'll substitute it here. So we got 31 with double 1 combination. So 31 will be substituting. For now, it will be substituted here, guys. So after that, we'll be splitting once we reach the more than 4. Fine. So after that, we got again 7 with 1, 1. And we got 9 with 0, 1. We got 20 with 0, 0. So here we got 0, 0. Again, we got 20 here. Fine. So once we got 20, we need to again subdivide, guys. So now the subdivision will be done for this 0, 0. So the next subdivision will be what, guys? It will be triple, 3 numbers. So it will be 1, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0. Is that correct? Yeah. 1, 0, 1, 1, 1, 0, 1, 1. We need to have 8, guys. 1, 2, 3, 4, 5, 6, 7, 8. Okay. So what are the combinations with triple 0? Here, okay, just to go back. Here we are having a triple 0. And 24 is also triple 0. Is that so? We are having 16 and 24. Let me check it guys. So that, yeah, 16 and 24. Yeah, here is the answer guys. It is 16 and 24. I did correct. So it is nothing but for 000 we are having 16 and 24, and the ones combination didn't divide yet. So we just continuing the same combinations of 1 1, 31, 7 and 9. Fine. And the combinations of 1 0. So while drawing, you draw it. I will just showing this guys so that you will have a clear idea. So the so guys, it is 16 and 24. I did correct. So it is nothing but for 000 we are having 16 and 24, and the ones combination didn't divide yet. So we just continuing the same combinations of 1 1, 31, 7 and 9. Fine. And the combinations of 1 0. So while drawing, you draw it. I will just showing this guys so that you will have a clear idea. So the combinations with 1 0. So what are ending with? Sorry, 0 1 0. So this is not 0 1 0. 0 1 0, 10 and 26. 26 is at end, right? So till where did we insert? We inserted till 20 only. So this will be having only 10. Right? Okay, I think just give me a second. Let me just analyze it. Okay, 6 to 22 and 10. We are having 3 seems. 6. Okay, okay, I understood. Here we need to divide this 0 0, right? So there is no need of dividing this 0 1. So we'll be having the combination state of this 0 1. So please understand this because I'm also a bit confused with these things now. Okay, so here we divided only 0 0. So the requirement is only dividing 0 0. So now we divided 000 and 1 0 0. So we got two different records for these two things. Whereas for these two, for 0 1 we didn't split, so it will be the same. So for 0 1 we are having, sorry, 1 0 we are having 6. Confused with these things now. Okay, so here we divide. So please understand this because I'm also a bit confused with these things now. Okay, of this 0 1. So please understand this because I'm also a bit. So here we need to divide this 0 0, right? So there is no need of dividing this 0 1. So we'll be having the combination state of this 0 1. So please understand this because I'm also a bit confused with these things now. Okay, so here we divided only 0 0. So the requirement is only dividing 0 0. So now we divided 000 and 1 0 0. So we got two different records for these two things. Whereas for these two, for 0 1 we didn't split, so it will be the same. So for 0 1 we are having, sorry, 1 0 we are having 6, 22 and 10. So here we'll be having 6, 22 and 10. Don't forget, I'll be just going through the thing that I have written in the book so that you'll be having a clear idea. Whereas 0 0, 1 0 0, where it is 1 0 0 we are having 4 and 20. So here we are having 4 and 20. Fine, so I'll just open the book so that you'll be clear. Okay. So till here, I'll just going through again the problem once we are done, guys. So after that, we inserted 26. So the code of 26, did I okay no? So the code of 26 is 101. So where is 101? Here it is 101. So we need to insert 26. Okay, 101. So 101 is ending with 1. So we need to insert 26 at this position. But I inserted here. So I think I did a mistake here again. I inserted in 010. So it should be inserted here, and here the overflow occurs, guys. So once here the overflow occurs, we need to divide this into two conditions now. Okay, so I'll be just doing it. Don't worry. Okay, so I substituted it here and I did it here. So for now, let us change the question. That will be better. So it should end with 010. So what's the value? Is nothing but 2, right? 10 and 1 as 0 1 and 1 1. So basically this will be considering as a single list only. Only for these two will be considering as separate lists. So that's the reason why we got separate list here and single list here. So after that insert 24 and 10. So we inserted 24 in the above and 10 in the below according to 0 0 and 1 0 records. Fine. So after that we inserted 31, 7 and 9. So those here are allocated in the combination with ending 1 only. Fine. So after that we inserted 20. So 20 got here and again the overflow occurred. So here we are dividing 0 0 as 000 and 1 0 0. Fine. So that's the reason why we got separate records for those two. But we continue the same records for 0 1 combination. So we are having 0 1 and 0 1 here. So 0 0 and 1 0 1 we have the same combination. 6, 22 and 10 the same combinations continued, and the ending one we continue the same combination 31, 7, 9. After that we continue with 26. Here I substituted 2 as I just wrote the combination wrong. So that's the reason why we substituted 2. So we substituted 2, we got overflow and then we divided.
Dear students, welcome to Bits Meshes. इस वीडियो में एक्सप्लेन करने जा रहा हूं कांसेप्ट ऑफ हैशिंग. तो हैशिंग से रिलेटेड जितने भी इंपॉर्टेंट पॉइंट है वो मैं आपको इस वीडियो में एक्सप्लेन करूंगा. Dear students, welcome to Bits Meshes. इस वीडियो में एक्सप्लेन करने जा रहा हूं कांसेप्ट ऑफ हैशिंग. तो हैशिंग से रिलेटेड जितने भी इंपॉर्टेंट पॉइंट है वो मैं आपको इस वीडियो में एक्सप्लेन करूंगा. हैशिंग जो है, अगर हम कॉम्पिटिटिव एग्जाम की बात करें ना, तो जैसे गेट के एग्जाम है, नेट के एग्जाम है, डिफरेंट
Orange, it will recognize it, right? Yes. Also say the output, it will give you the visible, right? So with the 2, Hello guys, we are back with our next tutorial. In this tutorial, let us go through error detection and techniques, guys. Okay, so basically what is error? Hello guys, we are back with our next set of tutorials. In this tutorial, let us go to start the fourth unit of database management system, guys. So in this unit, we'll be covering all the topics of indexing, hashing, and transactions. So we'll be covering these three are the main topics which we are going to cover in this whole series, guys. Okay, so basically what is indexing? So we'll be starting first with indexing, then hashing, and then transactions. Okay, so basically what is hashing? So what is indexing? So I hope everyone knows the word meaning of index. So basically every book will be having an index. So what is the use of that index? To specify the whole book info in a small sheet of paper or in 2-3 pages, right? So we'll be having the main topic, the page number. Main topic, the page number. So let us take an example of a textbook better. Okay, so each and every textbook will be having a particular index. It is going to have the topic names with page numbers. So similarly, to access data fastly, we will be using the concept of indexing in database, guys. So to store the records, to access them really faster, we'll be using this concept of indexing. Okay, so basically what is index? So index is a file that helps you or helps the operating system to find the records quickly. I hope everyone got a clear idea on what is the meaning of index. Okay, so indexing is a data structure to efficiently retrieve records from the database files based on the attributes. Attributes are nothing but your required things, like you want to get the details of this particular student or this branch student's details. So all those will be collaborated and stored in particular indexes, and all the things will be happening. Guys, don't worry, we'll be going through them. On which the indexing has been done. It is similar to our books which we use. Fine. Okay, so basically indexing can be represented in two ways, guys. So those are nothing but mainly these are the two types which you can represent indexes. Those are nothing but sparse index and dense index. Okay, so again the main divisions will be types of indexing are divided to single level indexing and series, guys. Okay, so basically what is indexing? So we'll be starting first with indexing, then hashing, and then transactions. Okay, so basically what is hashing? So what is indexing? So I hope everyone knows the word meaning of index. So basically every book will be having an index. So what is the use of that index? To specify the whole book info in a small sheet of paper or in 2-3 pages, right? So we'll be having the main topic, the page number. Main topic, the page number. So let us take an example of a textbook better. Okay, so each and every textbook will be having a particular index. It is going to have the topic names with page numbers. So similarly, to access data fastly, we will be using the concept of indexing in database, guys. So to store the records, to access them really faster, we'll be using this concept of indexing. Okay, so basically what is index? So index is a file that helps you or helps the operating system to find the records quickly. I hope everyone got a clear idea on what is the meaning of index. Okay, so indexing is a data structure to efficiently retrieve records from the database files based on the attributes. Attributes are nothing but your required things, like you want to get the details of this particular student or this branch student's details. So all those will be collaborated and stored in particular indexes, and all the things will be happening. Guys, don't worry, we'll be going through them. On which the indexing has been done. It is similar to our books which we use. Fine. Okay, so basically indexing can be represented in two ways, guys. So those are nothing but mainly these are the two types which you can represent indexes. Those are nothing but sparse index and dense index. Okay, so again the main divisions will be types of indexing are divided to single level indexing and dynamic multi-level indexing, guys. Okay, so in this already I told you about these are the two indexing types, and we are further having primary index, cluster index, and secondary index. And in dynamic we are having BP and deep tree. Fine, so these are all the types of indexing which we'll be covering. We'll be covering these two in this tutorial, guys. And next tutorial we'll be going through these three, and after that we'll be going through individually in one tutorial these two things. Fine. Okay, so the first thing that you'll be asking me is that I told you about index. Fine. So now your question will be, what is a single level index? So you'll be having only a single level of indexes, guys. Okay, so if you ask me how can we represent it or how can you show it? Okay, so better let us take a small example so that you'll realize. Okay, so let us assume this is our index. Okay, so this is our first index, right? So this is not having any subdivisions, or this is not a subdivision of any other index. So this is the only index, and this is the only database which we are having. So this we are having only single, right? So this is the first level and the only level. So this is nothing but a single level. Whereas the multi-level will be in this way. See here, we are having two indexes, right? So let us assume this is our index. Okay, so this is our first index, right? So this is not having any is our. So better let us take a small example so that you'll realize. Okay, so better let us take a small example so that you'll realize. Okay, so let us assume this is our index. Okay, so this is our first index, right? So this is not having any subdivisions, or this is not a subdivision of any other index. So this is the only index, and this is the only database which we are having. So this we are having only single, right? So this is the first level and the only level. So this is nothing but a single level. Whereas the multi-level will be in this way. See here, we are having two indexes, and for these two indexes, one more index is pointing. So level 1, level 2, we are having two. So we can have multiple levels. So these type are called as multi-level indexing. Fine. Okay. So now let us first go to sparse index. Guys, please remember these two definitions are really important, guys, because we'll be using these two in these three things. So that's the reason why you have to be perfect with them. Okay. So sparse index. In index that contains an entry for each block. So here we are not going to have the data or the index for each and every record. We'll be having them for a particular block. For these two, one. For these two, one. Like that. Once you're going to example, you'll have it clear, guys. Don't worry. Okay. So remember, sparse means each block. Fine. Okay. So if you want a small example of one more thing, guys. So even the sparse index. Okay. These two not means an entry for each block. So that's the reason why you have to be perfect with them. Okay. So sparse index. In index that contains an entry for each block. So here we are not going to have the data or the index for each and every record. We'll be having them for a particular block. For these two, one. For these two, one. Like that. Once you're going to example, you'll have it clear, guys. Don't worry. Okay. So remember, sparse means each block. Fine. Okay. So if you want a small example of one more thing, guys. So even the sparse indexing is applicable for the fields which are ordered. This word also will be observing really frequently, guys, in this whole chapter. Okay. So they should be ordered in ascending or descending. They should not be in random order like 20, 30, 70, 10, 5, 6, 50, 100, 10 like that. They should not be in reverse order or anything like that. It should be ascending or descending. That's it. Fine. Okay. So if we take a small example of a small database. So let us assume this is our database. So let me write it here. DB. So this is our database. In that we are having some records about the student details. Assume. So we are having student number, student name, and his fees. Okay. So here what we are representing as is sparse index, right? So sparse. Remember, S means E. So if you have any of your friends' names, please remember in this way. So SE. Fine. Okay. So sparse means each block. E. Fine. Student database. So let me write it here. DB. All example. It should 50, 100, 10 like that. They should not be in reverse or 10, 30. You'll be observing really frequently, guys, in this whole chapter. Okay. So they should be ordered in ascending or descending. They should not be in random order like 20, 30, 70, 10, 5, 6, 50, 100, 10 like that. They should not be in reverse order 5, 6. Each block. So here we are not going to have the data or the index for each and every record. We'll be having them for a particular block. For these two, one. For these two, one. Like that. Once you're going to example, you'll have it clear, guys. Don't worry. Okay. So remember, sparse means each block. Fine. Okay. So if you want a small example of one more thing, guys. So even the sparse indexing is applicable for the fields which are ordered. This word also will be observing really frequently, guys, in this whole chapter. Okay. So remember, sparse means each block. Fine. Okay. So if you want a small example, each example you'll have it clear, guys. Don't worry. Okay. So remember, sparse means each block. Fine. Okay. So if you want a small example of one more thing is, so even the sparse indexing is applicable for the fields which are ordered. This will also be observing really frequently in this whole chapter. Okay, so they should be ordered in ascending or descending. They should not be random order like 20, 30, 70, 10, 5, 6, 50, 100, 10 like that. They should not be in reverse order or anything like that. It should be ascending or descending. That's it. Fine. Okay, so if we take a small example of a small database, so let us assume this is our database. So let me write it here, DB. So this is our database. In that we are having some records about the student details. Assume. So we are having student number, student name, and his fees. Okay. So here what we are representing as this sparse index, right? So sparse. Remember, S means E. So if you have any of your friends' names, please remember this way. So SE. Fine. Okay. So sparse means each block. Fine. Okay. Sparse is B. Here this will work. Each block. Sparse means each block. So these blocks are divided. So a pointer that is nothing but a block pointer will be representing each block a single element. So here 10, here 30, here 50, here 70. So assume that this is your first chapter. You're having subtopics. It will just show in the first page number of the chapter and last page. That's it, right? So in that way, only the first serial number 10 pointing this, and the second block 30 is pointed by this, 50 pointed by this, 70 pointed by this. So in this way, the sparse index works. Guys, once you understand the basics, I'll be going a bit fast. Only for this lecture will be a bit slow, guys, so that you understand it. If you don't know the basics, it will be tough for you. Okay? So I hope everyone got a small idea on sparse index. So now let us go to dense indexing. So an index that contains entry for each record, dr. Okay, fine. So each record will be having. So here there is a plus point is that it is applicable for non-ordering also. So the numbers can be in any order, like 90, 10, 50. In that way, ascending or descending or any random order will also be working. Fine. Okay. So this is a small example. Here we are having the database again. So I think I forgot to write about DB. Please remember to write, guys. Okay. So serial number we are having serial name and fees. Sorry, serial number, student name, and fees. So each record is having a particular index. Fine. At a time we are pointing this 20, pointing this 30 like that. So in this way we can access it really easy. This is not so efficient, guys, because we are having, if there are 100 records, we need 100 entries. So when we compare dense and sparse, will be playing an efficient role. So I hope everyone got a small idea on this. So in the next tutorial we'll be going to primary indexing, guys. So let us be in the next tutorial. Thank you. Thanks for watching. Hello guys, we are back to the next tutorial. In this tutorial, let us go through primary indexing. So in the last tutorial, we have gone through basics of indexing, and we have also gone through the sparse index and dense index. So now let us go through primary indexing. So primary indexing, please remember the main things. Like just all the types of indexing will be having 2 to 3 key things that you should remember. If you remember that, you can write the example, you can write it clearly on your own. It's really easy. Fine. Primary indexing, an index that is built on ordering and key field. So you may ask me that what is this key field? So in integrated construction, everywhere you have learned about primary key, right? Primary key, we call it and shortcut, and we learned it, right? So it will be having a unique value and it will never be null. So the same properties should be there for a particular field, and that should be in ordering. So that is nothing but your primary indexing. So I hope everyone got a small idea on this. Okay. So further moving on, this method is most efficient and allows a sequential file access. So I hope everyone got a small idea on this, guys. Okay. So basically, primary indexing you can do it in 2 different ways, guys. Those are nothing but your dense index, using dense index and using sparse index also. Fine. Okay. So here we are having the. Okay, let us first go to sparse index for dense, which is easy for you. So let us go to dense. So once you hear the word D, you should remember R. So D are short for doctor, right? Okay. So assume that doctor, you are a doctor, your father is a doctor, or someone in your family is a doctor. So DR. So if it is dense for each record, fine. So write, sorry for that. So write serial numbers, record points. Okay, first you write in the database, right? Database. So initially in database you have serial number, student name, fees. So your student number will be the key as it will be unique. Whereas student name can repeat, right? So if your name is Raju, your friend name may also be Raju. It may and same. Okay. So this is possible. Whereas serial number. If your number is 1, can your number be 1? Okay, let's say one more example. So let us say serial number is your Aadhaar card number, or your driving license code, or your bank account number. So those things will never repeat, right? So those things will be your key fields. So according to those, you'll be showing your index. Here we are using dense index. So each and every record will be having its own index. So here index 1, we are having 1, 2, 3, 4. So each and every record is having its own index. Fine. Whereas secondary index, here we'll be dividing the database into some blocks, right? So each 2, 3 records will become each block. So that this is more efficient when we compare with this guy. It is easy to implement, easy to find, but this is more efficient because we'll be having some less number of records in our index. Okay. Fine. So in this way we'll be indicated. So I hope everyone got a small idea on primary indexing. So now let us go through cluster indexing. So cluster indexing is something opposite to this. It is here we'll be dividing the database into some blocks. Whereas secondary index points. Okay, first you write. So right. Okay. So here we are having dense index and using. So that is nothing but your primary indexing. So I hope everyone got a small idea on this. Okay. So further moving on, this method is most efficient and it is having the ordering and key field. So you may ask me that what is this key field? So in integrated construction, everywhere you have learned about primary key, right? Value and it will never R. So once you hear this, guys, okay. So basically primary indexing you can do it and using sparse index too. Sparse index for dense, which is easy for you. So let us go to dense. Having the okay, let us allows a sequential file. So basically primary. So according to each and every record is built on order, the topic to be given as 1. There is a possibility that it will be given 1.1. If it is further divided, 1 topic to be given as. Okay, let's say one more example. So let us say serial number as your Aadhaar card number, or your driving license code, or your bank. So because we'll be having some less number of records in our index. Okay, fine. So in this way we'll be indicated. So I hope everyone got a small idea on primary indexing. So now let us go through cluster indexing. So cluster indexing is something opposite to primary indexing. Okay, so each and every indexing can be represented in both the dense and sparse, guys. So mostly I'll be using dense because dense. Sorry, mostly I'll be using sparse because sparse is better when compared with dense. So that is why I want only dense. So cluster index, an index that is built on ordering, same as primary, but non-key. So here non-key means that it can be anything. It can repeat. There are multiple options for it. It can repeat. It can have duplicates, and there are many options for it. Fail. So fine. So this is our database. So try to write as DB so that the value will be having divided. So these are the few details which are given. So according to that, we have divided them into blocks. Fine. So each block is having. So luckily here we are having for both 1 for 1. Here 2, 3 for 2. But here we are having 4. Right. Remember one thing. In cluster index, if we are having repetition, see here 1, 1. We should never have a repetition in our index. Fine. So is there any chance for a particular topic to be given as 1? There is a possibility that it will be given 1.1. If it is further divided 1.1 again, they will be given 1.1 also in that way. But they will never repeat the thing, right? So in that way, you should never repeat the things here. So here the common one is 1 for 1, 2. Here 2 is already allotted to this only. So that is why I skip 3 and we have directly given the pointer to 4. Whereas 4 is already available, so I there is no need to find this. So I hope everyone got a small idea on this. Okay. So now let us go to secondary indexing. Guys, remember you can draw this cluster index. You can also do it with the dense indexing also. Okay. Okay. So the thing is that dense indexing you need to remember that the given should be in a particular order. Fine. Okay. So now let us go to secondary index. So secondary index. So secondary index is also having its own rules, but it is a bit modified than both primary and cluster index. So in primary and cluster we are using ordering, right? So here it is non-ordering and it can be key or non-key. So there are 2 cases in this. One can be key and the other cannot be a key field. Fine. Okay. So here I assume that it has a key field. Non-ordering plus key field. So again this is our database. Fine. Okay. So here we are not having any repetitions. So that is nothing but your key presentation. So here we will be having different records. So here we will be showing them. But remember, here inside your database they may be in any order. But when you are showing them in the index, they should be in ascending order. Please remember that. Fine. Okay. But when you are showing them in the index, they should inside your there are 2 cases. So here it is non-key and cluster guys. So in primary and cluster we are using ordering, right? So here it is non-ordering and it can be key or non-key. So there are 2 cases in this. One can be key and the other cannot be a key field. Fine. Okay. So here I assume that it has a key field. Non-ordering plus key field. So again this is our database. fine, okay. So here we are not having any repetitions, so that is nothing but your key presentation. So here we will have different records, so here we will be showing them, but remember, here inside your database they may be in any order, but when you are showing them in the index, they should be in ascending order, guys. Please remember that, fine, okay. So here also I use the sparse indexing. Similarly, just remember, whenever there is non-ordering, there is no chance for primary, guys. Sorry, there is no chance for dense indexing, fine, okay. So here also we have non-ordering and non-key, so in this way you will represent, here we have non-key, so we can have repetitions 1, 2, 2, 5, 3. So I hope everyone got a small idea on this, so next video we will go into multi-level indexing. Thank you, thanks for watching. Sparse, because sparse is better. If we are having repetitions here, it is easy to implement, easy to find, but this is more efficient because we have some less number of records in our index, okay. Fine, so in this way we will be indicated. So I hope everyone got a small idea on primary indexing. So now let us go through cluster indexing. So cluster indexing is something opposite to primary indexing is. Okay, so each and every indexing can be represented in both the dense. Okay, let's take one more example. So it doesn't serial number or Aadhaar card number or your driving license code or your bank account number. So those. So initially in database you have serial number, student name, fees. So your student number with the key as it will be unique. Whereas student name can repeat, right? So if your name is Raju, your friend name may also be Raju. Pick me and same. Okay, so this is possible. Whereas serial number. If your number is 1, can your number be 1? Okay, let's take one more example. So it doesn't serial number or Aadhaar card number or your driving license code or your bank account number. So those things will never repeat, right? So those things will be your key fields. So according to those you will store in your index. Here we are using dense index. So each and every record will be having its own index. So here at index 1 we are having 1, 2, 3, 4. So each and every record is having its own index, fine. Whereas secondary index, here we will be dividing the database into some blocks, right? So each 2, 3 records will become each block. So that this is more efficient when we compare with this guy. It is easy to implement, easy to find, but this is more efficient because we have some less number of records in our index. Okay, fine. So in this way we will be indicated. So I hope everyone got a small idea on primary indexing. So now let us go through cluster indexing. So cluster indexing is something opposite to primary indexing is. Okay, so each and every indexing can be represented in both the dense and sparse guys. So mostly I will be using dense because denser. Sorry, index. So here index 1 we are saying. Okay, so this is possible. Whereas serial number. If your number is 1, can your number be 1? Record point. Okay, first you will get in the database, right? Database. So initially in database you have serial number, student name, fees. So your student number with the key as it will be unique. Whereas student name can repeat, right? So if your name is Raju, your friend name may also be Raju. Pick me and saying. Okay, so this is possible. Whereas serial number. If your number is 1, can your number be 1? Okay, let's take one more example. So it doesn't serial number or Aadhaar card number or your driving license code or your bank account number. So those things will never repeat, right? So those things will be your key fields. So according to those you will show in your index. Here we are using dense index. So each and every record will be having its own index. So here index 1 we are having 1, 2, 3, 4. So each and every record is having its own index, fine. Whereas secondary index, here we will be dividing the database into some blocks, right? So each 2, 3 records will become each block. So that this is more efficient when we compare with this guy. It is easy to implement, easy to find, but this is more efficient because we will be having some less number of records in our index. Okay, fine. So in this way we will be indicated. So I hope everyone got a small idea on primary indexing. So now let us go through cluster indexing. So cluster indexing is something opposite to primary indexing is. Okay, so each and every indexing can be represented in both the dense and sparse guys. So mostly I will using dense because denser. Sorry, mostly I will using sparse because sparse is better when we compare with dense. So that is why I draw only dense. So cluster index, an index that is built on ordering, same as primary, but non-key. So here, non-key means that it can be anything, it can repeat. There are multiple options for it. It can repeat, it can have duplicates, and there are many options for it. Failed. So fine. So this is our database. So try to write that DB so that the value will be having created. So these are the few details which are given. So according to that, we have divided them into blocks. Fine. So each block is having, so luckily here we are having for both 1, so 1. Here 2, 3 for 2. But here we are having 4. Right? Remember one thing. In cluster index, if we are having repetitions here 1, 1. We should never have a repetition in our index. Fine. So is there any chance for a particular topic to be given as 1? There is a possibility that it will be given 1.1. If it is further divided 1.1 again, they will be given 1.1 also in that way. But they will never repeat the thing, right? So in that way, you should never repeat the things here. So here the common is 1, so 1, 2. Here 2 is already allotted to this only. So that is why I skip 3 and we have directly given the pointer to 4. Whereas 4 is already available, so there is no need to find this. So I hope everyone got a small idea on this. Okay. So now let us go to secondary indexing. Guys, remember you can draw this cluster index. You can also do it with the dense indexing also. Okay. Okay. So the thing is that dense indexing you need to remember that to given should be in a particular order. Fine. Okay. So now let us go through secondary index. So secondary index. So secondary index is also having its own rules, but it is a bit modified than both primary and cluster index. So in primary and cluster we are using ordering, right? So here it is non-ordering and it can be key or non-key. So there are two cases in this. One can be key and the other cannot be a key field. Fine. Okay. So here I assume that it has a key field. Non-ordering plus key field. So again this is our database. Fine. Okay. So here we are not having any repetitions. So that is nothing but your key presentation. So here we will have different records. So here we will be showing them. But remember, here inside your database they may be in any order. But when you are showing them in the index, they should be in ascending order. Please remember that. Fine. Okay. So here also I use the sparse indexing. Similarly, just remember. But remember, here inside your database they may be in any. So that it has a key field. Non-ordering plus key field. So again this is our database. It has a key field. So in primary and cluster we are using ordering, right? So here it is non-ordering and it having its own topic to be given our index. It can be anything, it can repeat. There are multiple options for it. It can repeat, it can have duplicates, and there are many options for it. Failed. So fine. So this is our database. So try to write as DB so that the value will be having created. So these are the few details which are given. So according to that, we have divided them into blocks. Fine. So each block is having, so luckily here we are having for both 1, so 1. Here 2, 3 for 2. But here we are having 4. Right? Remember one thing. In cluster index, if we are having repetitions here 1, 1. We should never have a repetition in our index. Fine. So is there any chance for a particular topic to be given as 1? There is a possibility that it will be given 1.1. If it is further divided 1.1 again, they will be given 1.1 also in that way. But they will never repeat the thing, right? So in that way, you should never repeat the things here. So here the common is 1, so 1, 2. Here 2 is already allotted to this only. So that is why I skip 3 and we have directly given the pointer to 4. Whereas 4 is already available, so I just no need to find this. So I hope everyone got a small idea on this. Okay. So now let us go to secondary indexing. Guys, remember you can draw this cluster index. You can also do it with the dense indexing also. Okay. Okay. So the thing is that dense indexing you need to remember that the given should be in a particular order. Fine. Okay. So now let us go to secondary index. So secondary index. So secondary index is also having its own rules, but it is a bit modified than both primary and cluster index. So in primary and cluster we are using ordering, right? So here it is non-ordering and it can be key or non-key. So there are two cases in this. One can be key and the other cannot be a key field. Fine. Okay. So here I assume that it has a key field. Non-ordering plus key field. So again this is our database. Fine. Okay. So here we are not having any repetitions. So that is nothing but your key presentation. So here we will have different records. So here we will be showing them. But remember, here inside your database they may be in any order. But when you are showing them in the index, they should be in ascending order. Guys. Please remember that. Fine. Okay. So here also I use the sparse indexing. Similarly, just remember, whenever there is non-ordering, there is no chance for primary guys. Sorry, there is no chance for dense indexing. Fine. Okay. So here also we are having non-ordering and non-key. So in this way you will be presenting. Here we are having non-key. So we can have repetitions 1, 2, 2, 5, 3. So I hope everyone got a small idea on this. So next video we will go to multi-level indexing. Thank you. Thanks for watching. Hello guys, back to the next tutorial. In this tutorial, let us go to multi-level indexing. So till now we are having only a single index, right? So single level of single index. Whereas now we will have multiple levels of index. So if you want a small example, we will have one index. So in that index we will be showing the values of another 2 indexes. So this process continues, and at the end you these are connected to your database. So I hope everyone got a clear idea. So if you just rotate the book in this way, and if you observe this, it is nothing but a tree structure, right? So that is the reason why whenever you are using multi-level index, the concept comes, the topics like B, B plus 3 comes into play. Okay, so now let us go to the definition. So here we will find multiple indexes. Yeah, that's what I told. As when we store large amount of data, it may result to larger indexes. So using another level of index may make it efficient, right? So if there are 1 lakh records, if you make it into 2 or multiple parts, it will be really easy for accessing, right? So that is the main concept of this multi-level indexing. So if you take a small example, this is a small example, guys. So this is going to be really short, don't worry. Okay, so here we are having the database with some indexes, sorry, some key values or non-key values with this serial number. We are having the student name, the student keys, fine. So this is the database and the index. We are having 2 separate indexes. For the first 2 blocks we are having this, and the next 2 blocks we are having this. So these 2 indexes are stored again in an index. So whenever you need some record like 3, so it has an idea that after immediately before 4 the 3 will come, so it will travel to here. So 1, 2 means 2 is, sorry, 3 is greater than, sorry, 2 is less than 3, so it goes here. So it gets here 2, 3, so it will be fine. So this method is more efficient, right? So basically in this it is okay. Whenever there are some lakhs or thousands of records, this method will be used. So I hope everyone got a small idea on this. So the concepts in this will be B3 and B plus 3, guys. And the next tutorial will be starting B plus B3. So let us see the next tutorial. Thank you. Thanks for watching. Hello guys, till now we have completed the 1/3 of the chapter. We completed all the topics regarding to indexing, guys. So now let us start hashing. So hashing is a similar concept to indexing, but these two are completely different, guys. So basically hashing and hashing, this is an efficient method. It is 100% better than indexing, guys. So in hashing, you will be getting the exact disk location or the exact location for that particular record or particular file which you are searching. So hashing is an efficient technique to calculate the direct location of a data record on the disk without using the index structure. So here we will not use any kind of index structures. We will directly use the concept of hashing. Okay. So basically when you are learning about hashing, the 2 words which you recollect or which you hear always are nothing but the bucket and the hash function. So these two are the main important things which you will be hearing every time. So bucket, a hash file stores the data in bucket. So whatever the bucket consists, those are nothing but the hash files which store the data. So we're going to the formal definition of bucket object, guys. So what is hash function? So a hash function is a particular mapping function. If you give one input, it gives one input. So those two are unrelated. It calls a particular function. Fine. Okay. So now let us go to a small example, guys. So basically we give the input as Bob, John, and Mike. So these are nothing but the keys which we are giving. Fine. So whenever they are passed to the hash function, they are generated in some location address, right? So those are the exact location in which the files of their details are stored in the hard disk. So see, John is stored at 2001, like that. They are exactly stored. Fine. So I hope everyone got a small idea on this. Okay. So now let us go to static hashing. So static hashing. In static hashing, so basically I have to divide into static and dynamic. So this will start with static, and then we'll go to dynamic. So dynamic is most important, which is in our syllabus, and static, let us go to the interactions that we have with the area. Fine. Okay. So in static hashing, where a search key value is provided, so whenever a search key value is provided, the hash function always computes the same address. So you may ask me that what is the same address again, and you told that now only I have discovered that it will be generating an exact address, but it cannot be many such particular address, right? So you may ask me that way. So basically here we'll be computing some functions like mod value of x. So mod value of x, what will be the result? Guys, it will start from 0 to x minus 1, right? So this is nothing but the static hashing in which you will be getting the repeated values. So if we assume that we are calculating for mod 5, what will be the values from 0 to 4 only? So whenever you are considering for this value, you will be getting 10 by 5, you will be getting 0. Even if you do 5 by 5, you will be getting 0. So here the keys are different, but the address locations are same. So this is nothing but we will call them as collisions in hashing. Fine. So let's take a small example. If we want to generate the address location of a key using mod 5 hash function, so here the function is nothing but mod 5. So it always generates the same result, nothing but 0 to 4. So number of data buckets in the memory are statically remains constant. So in the bucket you'll be having only 0, 1, 2, 3, 4. So these will be your bucket values, and everything will be showing right here. So we'll be having multiple values. So these causes collision. So I hope everyone got a small idea on this static. So if we take example of mod 4, we'll be having 5 values, so nothing but 0 to 4. 0, 1, 2, 3, 4. So there are 5 values. So I hope everyone got a small idea on this. So in next tutorial we'll be going through dynamic hashing, and we'll also go through an example how we will such because that's also one of the most important questions which we will be observing in our question papers. So I hope everyone got a small idea on this. So in next tutorial we'll be going through dynamic hashing. Thank you. Thanks for watching. Hello guys, we're back to the next tutorial. In this tutorial, let us go through indexing and the differences between indexing and hashing, guys. So these two are the most important topics that we have discussed till now, guys. Till this episode or till this lecture, we have just gone through all these topics. Fine. Okay. So indexing. First, let us go to indexing. A data structure technique to efficiently retrieve the records. It's an efficient technique to retrieve the records from the database files based on some particular attributes. So we use the key, order, and all those things, right? So those are important attributes which is done using the help of indexing. So whereas hashing, an efficient technique to calculate the direct location. This is what we discussed, guys. So we'll be calculating the direct location of the data records on the disk without using the index structure. So that is the main difference between these two things. So I hope everyone got a small idea on this. So now let us continue. So indexing does not work well when there is a large database. Fine. So I hope everyone got a small idea on this. It does not work well for large database, whereas works well for large database. Hashing works really efficiently even if the database is really large for having many records. Fine. So indexing uses data references that holds the address of the disk blocks. We are having blocks with the values corresponding to the particular keys. Whereas here we will be using a mathematical function called hashing, guys. Hash function to calculate the different locations of the data records and on disk. So I hope everyone got the differences between the hashing and indexing. So in next tutorial we're going through a small technique of hashing which is called as bitmap indexing, guys. So let us see the next tutorial. Thank you. Thanks for watching. Indexing. So I hope everyone got a small idea on this. Fine. Primary indexing. An index that is built on ordering and key field. So you may ask me that what is this key field? So in integrated construction everywhere we have learned about primary key, right? Primary key, PK will call it in short, and we learned it, right? So it will be having the unique value and it will never be null. So the same properties should be there for a particular field, and that should be in ordering. So that is nothing but your primary indexing. So I hope everyone got a small idea on this. Okay. So further moving on, this method is most efficient and allows a sequential file access. So I hope everyone got a small idea on this, guys. Okay. So basically primary indexing you can do it in two different ways, guys. Those are nothing but your dense index, using dense index and using sparse index also. Fine. Okay. So here we are having the, okay, let us first go to sparse for dense, which is easy for you. So let us go to dense. So once you hear the word D, you should remember R. So D are short for doctor, right? Okay. So assume that doctor, you are a doctor, your father is a doctor, or someone in your family is a doctor. So DR. So if it is dense for each record, fine. So right, sorry for that. So write serial numbers, record point. Okay, first you write in the database, right? Database. So initially in database you have serial number, student name, fees. So your student number with the key as it will be unique. Whereas serial, sorry, student name can repeat, right? So if your name is Raju, your friend name may also be Raju. It may and same. Okay. So this is a possibility. Whereas serial number. If your number is 1, can anyone number be 1? Okay, let's take one more example. So bank account number. The record will be having its own index. So here at index 1, we are having 1, 2, 3, 4. So each and every record is having its own index, fine. Whereas secondary index, 2, 3 record, we implement easy, guys. So mostly I'm using dense because denser. Sorry, mostly I'm using sparse because sparse is better. Mostly I'm using so doctor or someone. So I hope everyone come back. Fine. So in this one we will indicate number of. So here index 1, we are having 1, 2, 3, 4. So each and every record is having its own index, fine. Whereas secondary index, here we will be dividing the database into some blocks, right? So each 2, 3 records will become each block, so that this is more efficient when we compare with this, guys. It is easy to implement, easy to find, but this is more efficient because we are having some less number of records in our index. Okay, fine. So in this one we will indicate. So I hope everyone got a small idea on primary indexing. So now let us go through cluster indexing. So cluster indexing is something opposite to primary indexing. Okay, so each and every indexing can be represented in both the dense and sparse, guys. So mostly I'm using dense because denser. Sorry, mostly I'm using sparse because sparse is better when compared with dense. So that is why I want only dense. So cluster index, an index that is built on ordering, same as primary, but non-key. So here, non-key means it can be anything, it can repeat. There are multiple options for it, it can repeat, it can have duplicates, and if there are many options for it, fail. So fine, so this is our database, so try to write that DB so that the value will be having clear. So these are the few details which are given. So according to that, we have divided them into blocks, fine. So each block is having, so luckily here we are having for both 1 for 1, here 2, 3 for 2, but here we are having 3 for, right? Remember one thing, in cluster index, if we are having repetitions here, 1, 1, we should never have a repetition in our index, fine. So is there any chance for a particular topic to be given as 1? There's a possibility that it will be given 1.1. If it is further divided 1.1, again, they will be given 1.1 also in that way, but they will never repeat the thing, right? So in that way, you should never repeat the things here. So here the common is 1, so 1, 2. Here 2 is already allotted to this only, so that's the reason why I skipped 3, and we have directly given the pointer to 4. Whereas 4 is already available, so I just no need to find this. So I hope everyone got a small idea on this. Okay, so now let us go to secondary indexing. Guys, remember you can draw this cluster index, you can also do it with the dense indexing also. Okay. Okay, so the thing is that dense indexing you need to remember that to give a should be in a particular order, fine. Okay. So now let us go to secondary index. So secondary index. So secondary index is also having its own rules, but it is a bit modified than both primary and cluster, guys. So in primary and cluster we are using ordering, right? So here it is non-ordering, and it can be key or non-key. So there are two cases in this. One can be key and the other cannot be a key field, fine. Okay. So here I assume that it has as a key field, non-ordering plus key field. So again, this is our database. Fine. Okay. So here we are not having any repetitions. So that is nothing but your key presentation. So here we are not index. So secondary index is also having its own rules, but it is a bit modified than both primary and cluster guys. So in primary and cluster we are using ordering, right? So here hello guys, we are back to our next tutorial. In this tutorial, let's go through the introduction of a B tree and we'll also solve a problem guys, so that we'll be having a clear idea. Guys, you should understand the thing that you should remember in this B and even B, the concepts are really same guys. There is not even a small change, there is only a small change that I'll be going to do. If I say it now, you'll be they can confuse it with it. Okay, so please understand what I'm saying really clearly because it's really important. Okay, so basically B stands for Bayes tree, or we will be also calling it as balanced tree, balanced research tree. Fine. Okay, so the aim of this balanced research tree is to build an index structure. So these topics all belong to indexing. Don't worry. Okay. Okay, so the representation of it will be in this way. So let us assume this is our root node. In that we'll be having multiple keys, and each key will be having their subtrees. So these are also in this format. They will also be having subtrees, and this process continues. So this is the basic representation. Sorry for that, of B and even B case trees. Fine. Okay, so now let us go through some properties of B tree. Remember, this are
Hi, the topic is B trees and B plus trees. This is one of the important topic and it's a difficult topic for the students to understand. This is useful in databases. What are the things that are required for understanding B trees and B plus trees thoroughly? This is the list of topics. If you understand all these things and if you know all these things, then you can understand what B trees and B plus trees are. Mostly people try to understand how insertion and deletion is done, just they try to learn the procedure without knowing everything. So this video will be a little lengthy. Reason I'm going to cover all these topics that are related to B and B plus trees and help you understand perfectly what B plus tree and B and B plus trees are. Let me read out the topics. Disk structure, how a disk looks like and how the data is stored on the disk. Then next, when you are storing data from databases, then indexing is used for faster searching. Then what is indexing, what is multi-level indexing. Then we will also discuss what are MV search trees and database searches are converted to B trees and then B plus trees. So this is a little bit lengthy, but I suggest you listen everything, go through it, then you'll never forget this topic. Let us start with the disk structure. Let's look at disk structure. Disk structure is like a platter on which the concentric circles are made. These are logical circles. This is not physical. And these circles are called as a track. So let us say this is track 0, track 1, track 2, and track 3. Then these pieces are called as sectors. So this is sectors and this is also sector. Like this. This is sector 0, sector 1, sector 2, sector 3, and 4, and 5. So this is divided into many tracks and sectors. The intersection portion of track and the sector, this one, or this one. All these intersecting positions, these are called as blocks. So any location on the disk can be addressed with track number and sector number. So the address on the disk, that is block address is mentioned in the form of track number and sector number. So like this, if I take this particular block, then this is track 1 and sector 0. This block, track 2, sector 1. So each block can have its address in the form of track number and sector number. And typically, the block size, we take it as 512 bytes. For study purpose, we take it as 512 bytes. It can be any size, it depends on the manufacturer of a disk. So we assume that every block is of 512 bytes. When the disk is read, when we read or write to and from the disk, we always read and write in terms of blocks. Now if I take just one block that is of 512 bytes, the beginning address, that is first byte is 0, and the last byte is 511, then each byte can have its own address that is called as offset. Let's say this is the 10th byte. So we can refer any one byte on the disk in terms of first of all block address, and inside that block we will take offset, that is the address of that particular byte. Every block we assume that address starts from 0 and last address is 511 equals to 512. So any address, any byte we can take as address, and that address is called as offset. To each particular byte on the disk, we should know track number, sector number, and the offset. Let's say in this particular block, this particular point I want to read, this suppose this is one byte. For reading that byte, I should know these three things. Then let's understand one more thing. This is mounted like this on a spindle, and the head post will also be there. So by spinning, it will change the sectors. By this arm movement of a header, that is reading the data from the disk or writing the data on the disk, by this movement, tracks are changed. So we can position a head in a particular track and in a particular sector by moving this post, that is head post, or spinning this one. So by spinning, sectors are changed. By moving head, tracks are changed. This is about the disk. Now the data on the disk is always stored in terms of blocks. Now noting, let us take this as main memory. usually call it as RAM. RAM is the technology, and the type of memory is main memory. We have other programs inside main memory, and the programs will access data. Suppose they're accessing the data from the disk, then the data from the disk must be brought into the main memory, and then only it can be accessed. And if any results are obtained, then the results are again written back onto the disk. So the data cannot be directly processed upon the disk; it has to be brought into the main memory and then accessed. This is one important point to understand. And one more time I tell you, organizing the data inside the main memory that is directly used by the program. Data inside the main memory that is directly used by the program, that is data structures. And organizing the data on the disk efficiently so that it can be easily utilized, that is dbms. So study of the methods or the approach used for storing the data in an efficient way there on the disk is all about dbms, designing, organizing everything. Now here, study on this one is data structures. Now let's move on to the next thing, how data is stored on the disk. Now let's know how the data is organized on the disk in the form of database. I have an example database table here with some columns and some rows. Let's say there are 100 rows. And how the data is stored on the disk in the form of blocks, already have studied that. And assume that the block size is 512 bytes. Now this table, the structure of the table is given here. There are no number of fields, I'm not showing them there, but here I have them all. So total there are 5 fields, and these are their sizes. Employee ID is of size 10 bytes, and this is of 50 bytes, and the department is 10 bytes, so on. So total it takes 128 bytes. Now it means each row size is 128 bytes. This each row is 128 bytes. Now when we want to store that table on the database, then in each block, how many rows can be stored? That is how many records can be stored. So number of records per block. So the block size is 512 and the record size is 128, so this is 4. It means we can store 4 rows of this table in one block. It means that these 4 rows will go into one block, and these 4 rows will go into next block. Every 4 rows are stored in one block, so one block can contain just 4 rows. As we have 100 rows here, there's 100 records here, then how many blocks are required? Then for 100 records, how many blocks? There are 100 records, and each block can contain just 4 records, so this is 25. So total 25 blocks are required for storing this database table on disk. Now, when this table is taking 25 blocks, imagine if you want to search for any particular record, you have it in a query. Select from employee table, as employee table, and I want so and so record for employee ID 5 or employee name Smith. If I'm searching, then how much time it will take? So the time depends on the number of blocks you're accessing. So for accessing this entire table, we have to access 25 blocks. So the number of block access is more, 25. Because the record may be present anywhere, we don't know where the record is present, so we have to search in the table. So for that, at most 25 blocks we have to access. We can access block by block and check for that particular record which we are looking for, but at most 25 blocks we have to access. Can we reduce this time? Yes. Now we will prepare an index for this database table. So index. In index what we will store? In index we will store a key, that is employee ID, and pointer. Pointer to it. In index what how much time it will take. So the time depends on the number of blocks you are accessing. So for accessing this entire table, we have to access 25 blocks. So the number of block access is more, 25. Because the record may be present anywhere, we don't know where the record is present, so we have to search in the table. So for that, at most 25 blocks we have to access. We can access block by block and check for that particular record which we are looking for, but at most 25 blocks we have to access. Can we reduce this time? Yes. Now we will prepare an index for this database table. So index. In index what we will store? In index we will store a key, that is employee ID, and pointer. Pointer to a record. So let's say employee ID 1, this is present here, and employee ID 2, this is present here, employee ID 3, this is present here. So we will have a pointer actually to the table inside the disk, inside the block. So we'll have a pointer to a record. So this is called as a record pointer. We will have a pointer to a record on the disk in the block. For each record we will have an entry inside the index. So this is called as an index. Next. Where do you store index? We will store index also on the disk only. Let's say in this block we are storing an index. This is for index. This is for the database table, and no record, no blocks are there because it's taking 25 blocks. Index is also kept on the disk. Now the question is how much space does index will take on the disk? Let's analyze. See, employee ID is 10 bytes. Then what about this record pointer? The pointer that we have taken here. Record pointer. Let us assume it is taking 6 bytes. So each entry size is how many bytes? 16 bytes. Each entry is taking 16 bytes. So how many entries are there here? 100 entries are there. Now the question is how many blocks required for this one? So entry size is 16 bytes, right? Now number of entries per block. So block size is 512 and each entry size is 16, so this will be 32. So it means we can have 32 entries in one particular block. So total how many entries are there here? 100 entries. So for 100 entries, 100 by 32. So how much is this? 3 point something. Let's say 3.2. Let's assume it's more than 3. So it means that we require 3 plus blocks for storing this index. So let's say 4 blocks are required for storing this index. Now whenever we want to search, we access index. So at most how many blocks we require? 4 blocks. 4 blocks of index. And once we got a particular key, let's just go and look for this. Using that address, I can access the record. So for accessing the record, I have to access one block. One block. So maximum 4 blocks of index and 1 block of database table. So for searching the index, at most how much time? 4 blocks. Then once you got the index entry, then go to that particular block of database. So that is 1 block. So total 4 plus 1 blocks are required for accessing any database record. for accessing any record, we have to access 4 blocks. That is just 5 blocks, not 35 blocks, because we don't have to look at the entire table. This is the benefit of index. Now we started to talk about multi-level index. Next, what if the index size is also growing? How? Instead of 100, now I have 1000 records. 1000 records means 250 blocks. Now here we require 4 blocks, now we require 50 blocks because there will be 1000 entities. Just managing it. When the rows were 100, we require 4 blocks. Now 1000, let's say 40 blocks are required. Just assume I'm not doing multiplications. Then the searching index itself is larger. So can we have an index above an index? Yes. Now how do you prepare this index? For every entry here, shall we have an entry in this next level index, high level index? No. For each block. So how many entries can possible in this block? 32 entries. So we will have one pointer to 32 entries of this particular index. Right? So let's say the starting key is 1. Right? Next key will be 33 and it will be pointing to the next block. So this is a sparse index. It will not have each entry for one entry here. Right? It will not have the same number of entries. It will have one entry for one next block. Here, shall we have an entry in this next level index, high level index? No. For each block. So how many entries can possible in this block? 32 entries. So we will have one pointer to 32 entries of this particular index. Right? So let's say the starting key is 1. Right? Next key will be 33 and it will be pointing to the next block. So this is a sparse index. It will not have each entry for one entry here. Right? It will not have the same number of entries. It will have one entry for one block of index. Now as I said, there are 40. Now again, what is the size of this one? Just 16 only. So how many are possible? 32 are possible in one block. Then for this particular index, how many blocks are required? Just 1 plus point something. Let's say 2. So 2 blocks are required. So this high level index can be stored just in 2 blocks. So data is 50 blocks. First level index 40 blocks. Then next high level index just 2 blocks. So search in 2 blocks. Once you get an entry, access the block here. Then once you get an entry, access the block here. So total how many blocks? 2 blocks from this side, 1 block from here, 1 block from here. So in this way, by adding one more level of index, we are reducing the number of block access. So this is the basic idea originating for B and B plus trees. I'll just draw multi-level index and then I'll show you how it looks like. Let's look at multi-level index once again. Suppose this is the main index. Now, this we need one more index. Suppose this is too large. Then how this will be having? It will be having a pointer to set of entries in the index. Then a pointer to set of entries in the index. I'm just taking randomly. I'm not drawing any counting and drawing. So this is having a pointer to these. Suppose this is also large. This is also large. Then you can have one more index which will have a pointer to set of entries and a pointer to set of entries. This is how we can go on adding multi-level index if the database table. So here's the database table and if size is growing, this index will grow and we'll have one more index, one more index. Adding multi-level indexes will reduce the number of block access. So if I just turn it around and see it like this. Next level index, then next level index. If I turn it around and see this is how the multi-level index looks like. Now what is the requirement of multi-level index? Shall we add the index by manually? Shall we check that the database size is growing and then we should add indices one by one? That's high level index. No. We want the high level index to be added automatically and deleted automatically. If this is increasing, table size is increasing and this index is increasing, then you add one more index. If you are deleting records, then the index size will reduce and then you remove the high level index. We want self-managed high level indexes. That's multi-level indexing. So the final thing is we want self-managed multi-level indexing. And that's how it gives the idea of B trees and B plus trees. So now you can see that this multi-level indices are looking like a tree. If I just turn this side up, then it looks like this. B trees and B plus trees are actually originating from M-based search trees. So next time we discuss what are M-based search trees, then finally we'll go to B trees and B plus trees. Let's talk about M-based search tree. See, for knowing about M-based search tree, let us recall about binary search tree, which is useful for searching purpose. So now we check that this is how the multi-level index looks like. Now, next level index. If I turn it around and see this is how the multi-level index looks like. Now what is the requirement of multi-level index? Shall we add the index by manually? Shall we check that the database size is growing and then we should add indices one by one? That's high level index. No. We want the high level index to be added automatically and deleted automatically. If this is increasing, table size is increasing and this index is increasing, then you add one more index. If you are deleting records, then the index size will reduce and then you remove the high level index. We want self-managed high level indices. That's multi-level indexing. So the final thing is we want self-managed multi-level indexing. And that's how it gives the idea of B trees and B plus trees. So now you can see that this multi-level indices are looking like a tree. If I just turn this side up, then it looks like this. B trees and B plus trees are actually originating from M-based search trees. So next time we discuss what are M-based search trees, then finally we'll go to B trees and B plus trees. Let's talk about M-based search tree. See, for knowing about M-based search tree, let us recall about binary search tree, which is useful for searching purpose. And for searching any key value, we start from the root, and if the key value is smaller, we go on the left hand side. If the key value is larger, we go on the right hand side. Like this is a binary search tree. If I'm searching for 15, then 15 is greater than this, I'll go to this side. 15 is smaller than this, I'll go to this side, and it is found. So we know that the smaller keys are arranged on the left side and the larger keys are arranged on the right side. This is what is done in binary search tree. In binary search tree, how many keys we can have per node? Just one key. And how many children each node can have? How many children? They can 2 children. Each node can have maximum 2 children. So that's why it's called as binary tree. Binary means 2 children. So it means can we have a tree with more than 2 children or more than 1 keys? Let's check. 20 and 50. These are 2 keys. Now this side I will have the keys which are smaller than 20, so that is 10 and 15. And here I will have the keys that are in between these two, that is 30, 35. And here I will have the keys that are greater than this, so that is 60 and 90. So yes, we can have a search tree like this also. This is search tree. This is the following idea of same as binary search tree. See, the keys are arranged such that they are in increasing order. So if you see the keys here, see first key is smaller than second key and smaller than third key. If you have more keys, they will be arranged like this. And if I'm searching for 30, then I'll start from here. 30 is greater than 20. 30 is less than 50, so it must be in this child. Come here, 30 is found. Next time we discuss. So I go to side and it is found. How many keys we can have per node? Just one key. And how many children each node can have? How many children? They can 2 children. Each node can have maximum 2 children. So that's why it's called as binary tree. Binary means 2 children. So it means can we have a tree with more than 2 children or more than 1 keys? Let's check. 20 and 50. These are 2 keys. Now this side I will have the keys which are smaller than 20, so that is 10 and 15. And here I will have the keys that are in between these two, that is 30, 35. And here I will have the keys that are greater than this, so that is 60 and 90. So yes, we can have a search tree like this also. This is search tree. This is the following idea of same as binary search tree. See, the keys are arranged such that they are in increasing order. So if you see the keys here, see first key is smaller than second key and smaller than third key. If you have more keys, they will be arranged like this. And if I'm searching for 30, then I'll start from here. 30 is greater than 20. 30 is less than 50, so it must be in this child. Come here, 30 is found. So no doubt the amount of time taken for searching is a little more than binary search tree, but the approach of searching is same. So these trees are called as M-way search tree. So what is this M-way? See how many keys it is having. In this example, it is having 2 keys. Then how many children it is having? So each node can have maximum 3 children. So this is 3-way search tree. This is 3-way search tree. This is called as 3-way search tree. So in this way, M-way search tree means what? A search tree in which each node can have at most m children. M-way search tree. So each node can have at most m children. So how many keys? M minus 1 keys. So M is based on the number of children, that is the degree of a node. So M-way search trees are the extension of binary search trees, you can say. Or else you can say binary search tree is the type of M-way search tree with degree 2. So you can have degree 3 also, degree 5 also, degree 100 also, degree 1000 also. So it means you can have 100 keys here, and each node can have 100 keys and 100 plus 1 children. So you can have any degree of search tree. This is about M-way search tree. Let's look at the node of M-way search tree. Like for binary search tree, how we prepare node is, we will have data here and 2 children. Then here you need more number of children. So let me draw the node for this one. If the M-way search tree is search tree ST I'm writing, it's suppose 4-way search tree. Means each node can have 4 children and 3 keys. Let me draw a node structure. This should be a child pointer. Pointed to the child, and this is key 1, and again this is a pointer to a child, and this is the key 2, and this is a pointer to a child, and this is key 3, and this is a pointer to a child. So 4 child pointers, so this is 4-way, and when it is a 4-way, then there can be 3 keys. That is M-way search tree, the node can have m minus 1 keys. So it's just like this. This is diagonal representation, and if you're making another structure, then the node structure looks like this. So if there are m children, then m minus 1 keys is required. Now next, can we use this search trees, these nodes structure, for preparing index? Let's see. So I will try to use this for making index. So let's check how we can do this. For 4-way search tree, where there can be 4 children. So this is child pointer. Okay. Now this is key 1, and this is next child pointer. Then this is key 2. Then this is the next child pointer, then this is key 3, and 4 child pointer. So child pointer 1, 2, 3, 4. Then what is this I'm adding? See, this after every key I have a pointer. This is nothing but, see, if you have keys here and you are taking an M-way search tree, benefit of M-way search tree as an index, then apart from the child pointer, you should have also a pointer to a record. That is a record pointer. So yes, we will also have a record pointer. So this is a record pointer. Record pointer. So we can utilize m-based search trees for indices, that is multi-level indices, like tree will have multiple levels. So for making multi-level indices, we can utilize tree will have then this is key 3, then this is and if you're making a data structure, then the node structure looks like this. So if there are m children, then m minus 1 keys is like that. Next, can we use this search trees? They can 4 child pointers, so this is 4-way, and when it is 4-way, then there can be 3 keys. That is 4-way, and this is pointed to a child. So 4 child pointers, so this is 4-way, and when it is 4-way, then there can be 3 keys. That is m search tree, and node can have m minus 1 keys. So it's just like this. This is diagrammatic representation, and if you're making a data structure, then the node structure looks like this. So if there are m children, then m minus 1 keys is like that. Next, can we use this search trees, these node structure, for preparing index? Let's see. So I will try to use this for making index. So let's check how we can do this. For 4-way search tree, where there can be 4 children. So this is child pointer. Okay. Now this is key 1, and this is the next child pointer. Then this is key 2. Then this is the next child pointer. Then this is key 3 and 4 child pointer. So child pointer 1, 2, 3, 4. Then what is this I am adding? See this. After every key, I have a pointer. This is nothing but, see, if you have keys here and you are taking an m search tree, benefit of m search tree as an index, then apart from the child pointer, you should have also a pointer to a record. That's a record pointer. So yes, we will also have a record pointer. So this is a record pointer. So we can utilize m search trees for, and you are taking an m search tree, benefit of m search tree as an index, then apart from the child pointer, you should have also a pointer to a record. That's a record pointer. Then what is this I am adding? See this. After every key, I have a pointer. This is nothing but, see, if you have keys here and you are taking an m search tree, benefit of m search tree as an index, then apart from the child pointer, you should have also a pointer to a record. That's a record pointer. So yes, we will also have a record pointer. So this is a record pointer. So we can utilize m-based search trees for indices, that is multi-level indices, like tree will have multiple levels. So for making multi-level indices, we can utilize m-based search tree, but the node structure should be like this. So just remember this node structure. See, keys are there and child pointer. So 4 4, so 4 child pointer, 3 keys, so 3 record pointers. For each record, key, there's a pointer to the record, Now, if we simply use m-based search tree, what will be the problem? And how we can overcome the problem and we introduce B trees. Now we are going. So we can utilize m-based search trees for indices, that is these nodes structure, for preparing index. Let us see. So I will try to use this for making index. So let us check how we can do this. For 4-way search tree, where there can be 4 children. So this is a child pointer. Okay. Now this is key 1, and this is the next child pointer. Then this is key 2. Then this is the next child pointer. Then this is key 3 and 4 child pointer. So child pointer 1, 2, 3, 4. Then what is this I am adding? See this. After every key, I have a pointer. This is nothing but, see, if you have keys here and you are taking an m-based search tree, benefit of m-based search tree as an index, then apart from the child pointer, you should have also a pointer to a record. That's a record pointer. So yes, we will also have a record pointer. So this is a record pointer. So we can utilize m-based search trees for indices, that is multi-level indices, like tree will have multiple levels. So for making multi-level indices, we can utilize m-based search tree, but the node structure should be like this. So just remember this node structure. See, keys are there and child pointer. So 4 degree 4, so 4 child pointer, 3 keys, so 3 record pointers. For each record, for each key, there's a pointer to the record, to the database record. Now, if we simply use m-based search tree, what will be the problem? And how we can overcome the problem and we introduce B trees. Now we are going towards B trees now. Till here we have discussed about m-based search tree. Now I'm taking you to B tree. And in B tree, we will use the same node structure. Just remember this. Again, I may not be showing you. This is the node structure that is followed in B trees. But first of all, let us know what is the problem with m-based search tree and how B trees are different from m-based search trees. Let us see how insertion is done in m-based search tree and what is its problem. Then we'll move on to B trees. For that, to make you realize the problem, I have taken 10-way search tree. 10 means degree 10. Means each node can have 10 children and 9 keys. And suppose I have to insert these keys. Let us see how I can insert. First 10. There is nothing. So I will create a node and insert 10. How many more keys I can have here? 8 more keys I can have here. But for inserting 20, I will create a new node as a child and insert 20. Then inserting 30, 10, that is smaller, 30 comes from right side, so I will not insert here, but I will come to this, and 20, 30 is greater than this, so I will insert 30 here. So I can insert like this also, but this is wrong. I should first fill up this node, then only I should think of creating next node. But there is no control on m-based search tree. You can insert as you like. So it means if I have n keys, then what will be the height of m-based search tree? N. So this will be too much time consuming. It becomes similar to linear search. That's the problem with m-based search tree. So what is the problem with m-based search tree? The creation process is not under any control. There are no guidelines for creation process. You can create as you like. If suppose you are creating it like this, then it's a waste of time. It will take a lot of time for searching. Then there must be some rules or guidelines for creating m-based search tree. Yes, those guidelines are called as B trees. So B trees are nothing but m-based search trees with some rules. Let us see what are those rules. I'll explain them. Let us see what are B trees. B trees are nothing but m-based search trees with some rules. So what are the rules? Let us see. See, the first thing. Every node you must fill at least half. Half what? If the degree is m by 2 children must be there. So m by 2 seal value is taken, not floor, m by 2. Means if degree is a 10, means 5 children must be there for a node. Every node must have 5 children. Then only you think of creating new node. That's what, to control the height of m-based search tree. This is the rule. You can create a next node only if the current node is at least half filled with children. This is one. M by 2 children must be there. Then second thing, how we can impose this condition on the root? We cannot impose this condition on the root. If we impose, then we cannot insert even a first value also. So root can have minimum 2 children. So root means the first one. So first node can have minimum 2 children, right? So it means it can have just 1 key also, no problem. But what about all other nodes? They must have at least half of the children. This is the conditions, 2 conditions. Now third conditions. Then the third rule is all leaf nodes must be at same level. All leaf at same level. That's it. These are the 3 things if you are following for creation of a m-based search tree. So actually we are creating B tree. And one more important thing here is that the creation process is, fourth point is, the creation process is bottom up. Creation process is bottom up. So now I will take some keys and I'll show you how a B tree is generated from bottom up. So for that, I'll not take a 10-way search tree. I'll take a small degree tree and show you how a B tree is created. In other words, how insertion is done. We will create a B tree of degree 4, means each node can have 4 children and 3 keys. So I have taken some of the keys here, then I'll be inserting more and more nodes. So I'll add more keys afterwards. Let us start. First, there is no node at all. First key I'm inserting. So that is 10. First key. So it can have how many children? 2 children. And as per the multi-level index one, we said that it can have one record pointer. The next 20. 20 will be inserted here. That is greater than 10. 40 is inserted here. Next is 50. There is no space for 50. Already 3 keys are there. Degree is 4, so we cannot insert 50. 50, there is no space. Then what we should do? Split this node and create one more node. So out of 10, 20, 40, and 50, 2 keys I will take this side, and 1 key I will send this side. 40 I will send it in the root. Then this is the left child, this is the right child. That's it. So when the node was filled, there was no free space. Then for inserting a key, we have split the node. Was filled, there was, so it can have how many children? So take how a B tree is created. In other words, how insertion is done. We will create a B tree of degree 4 in which each node can have 4 children and 3 keys. So I have some of the keys here, then I'll be inserting more and more nodes. So I'll add more keys afterwards. Let's start. First, there's no node at all. First key I'm inserting. So that is 10. First key. So it can have one children, 2 children. And as per the material index one, we said that it can have a record pointer. The next 20. 20 will be inserted here. That is greater than 10. 40 is inserted here. Next is 50. There's no space for 50. Already 3 keys are there. Degree is 4. So we cannot insert 50. 50. There's no space. Then what should do? Split this node and create one more node. So out of 10, 20, 40, and 50, 2 keys I will take this side, and 1 key I will send this side. 40 I will send it in the root. Then this is the left child, this is the right child. That's it. So when the node was filled, there was no free space. Then for inserting a key, we have split the node, and one of the key we have sent it on the root. Out of 4, including 50. Out of 4, 2 this side, 1 that side, 40 up. This is how splitting is done while creating a B tree, and you can see that the tree is going upwards. So that's it. It's created bottom up. And I was telling you that B trees are useful for implementing multi-level indexing. That if you say this is one first level index, then out of that is the second level index created automatically. If you add keys here, automatically this is created. Now let's see. I will add more keys here, then again you can see that this is growing. So let's continue. I will insert 3 more keys. Let's say 60. So 60 comes here. Then 70. 70 comes here. Then 80. 80. There's no space here. 80 should come here. There's no space. Then split again. Then what I should do? Including 80, 50, 60, 70, and 80. So 80 should go this side, and 70 should be in the root. That's the child. Now the tree looks like this. Then next I will insert 30. 30. 30 will come here. Then I will insert 35. There's no space for 35 here. Then split. So as there's no space, I will split this side. So out of 10, 20, 30, and 35. 35. This should go in the root, and the 10, 20 this side, and 35 on this side, right side, 35 on this side. Then who will go in the root? 30. So I will redraw it. 30, 40, and 70. I'll remove this. Yeah, watch it. This is the child, this is the next child, this is the child, and this is the child. This is what it looks like now. So whenever the node is becoming filled, we are splitting it, and we are sending one of the key in the pair. Now we try to fill a few more keys here, and let's see. I want to insert 5. So where 5 will come? 5 will come in the beginning. So 5, 10, and 20. Now I'm going to insert 15. 15, there's no space. So 5, 10, 15, and 20. There's no space for 15. Then arrange them in this order, then there's no space to split it. So for splitting, I will create one more node on this side. 5 and 10 this side, and 20 this side. Now 15 should go up here. This should go up. Right? So no point. You're thinking that why I'm sending third key. I want to send second key. Okay, that's your choice. So you can make it either left biased or right biased. So either way you can do that. Now it's left biased means it's more keys on the left side. So whichever one you want, you can take it. So 15 goes up, 20 on the side, and 5 and 10 this side. Now there's no space here also. So here also you split it. So out of how many keys? 15, 30, 40, and 70. So 15 and 30 this side, 70 that side, and 40 in the parent. So this will be on the side, this will be on the side. Now all these links will also change because we are splitting it. So this is on the side, this is on the side, this one. And I will draw it a little far from this one. 70, then 70 is left and 70 is right. So now you can see that 3 levels, 1, 2, 3. So 3 levels of indexes are created, and this is how B tree is generated by inserting keys. And the height of B tree is increasing, and this is same as multi-level index. So this is the creation process. So it's under control, and all these nodes are at the same level. So they are looking like more like index, and this is the same level. This is forming index, and other one is also index. So I've shown you how to insert and how to create a B tree. Now let's see how it's useful for data analysis. This minor things are very important and key points I'm showing you. As we discussed just now that every node will have a pointer to the child node as well as a record pointer. This 20 will have a record pointer, 5 will have a record pointer, 10 will have a record pointer, 15 will have a record pointer, 30 will have a record pointer. Every key will have a record pointer also that is pointing on the database. So this is useful for implementing multi-level index. Apart from the child pointer, this is a record pointer. So a B tree node can have what key, child pointer as a block pointer, and this is a record pointer. That's it. That's it about B trees. I did not show deletion. It depends how much you have understood from this one. Just reply me back, leave your comment, and if required, I'll prepare deletion also. Okay. Actually, I wanted to show you what's the application of B trees and B plus trees. So I have started my topic right from indexing and brought your. Here 15 is missing here. So 15 will be here also. 20. So 15 will have its copy here also. So there will be a record of 15 also, 20 also. Then 30, here will have a copy of 30 also, and 35. So what 40? 40 will have a copy here also. 40 will be having a copy here. So 40 and 50.
And also, इसमें how to insert the elements in the B tree. मतलब हम B tree को कैसे create करते हैं? तो देखो हमारे पास दिया हुआ है insert the following And also इसमें वापस आ गया इसमें एक्सप्लेन करने जा रहा हूं बीटी का इंट्रोडक्शन पार्ट तो देखो बीटी के बात करें तो इसको होता है डायनामिक मल्टी लेवल इंडेक्स मल्टी लेवल इंडेक्सिंग के ऊपर मैंने ऑलरेडी क्वेश्चन भी एक्सप्लेन किया हुआ है इसका आपको डिस्क्रिप्शन बॉक्स में मिल जाएगा जल्दी मल्टी लेवल इंडेक्सिंग हम करते हैं सेकेंडरी मेमोरी में हमारा पूरा डेटा है तो लेट्स से हमारे पास नंबर रिकॉर्ड्स है उन सारे रिकॉर्ड्स को हमने सेकेंडरी मेमोरी में डाल दिया अब मेमोरी के जितने भी डेटा डाला उसके कॉरस्पॉन्डिंग हम क्या बनाते हैं इंडेक्स बनाते हैं टाइप्स ऑफ इंडेक्सेस वाली सारे ऑलरेडी क्लेम किया हुआ है प्राइमरी इंडेक्स क्लस्टर सेकेंडरी इंडेक्स क्लास क्या होता है डेंस क्या होता है ये सब ऑलरेडी आपको लिंक में मिल जाएगा डिस्क्रिप्शन बॉक्स में लिंक दिए हुए हैं वो सारे इंडेक्स इंडेक्स पार्ट आपको उसमें मिल जाएगा अब होता है क्या जब हम डेंस बनाते हैं डेंस में होता है कि हर एक एंटिटी के लिए यहाँ पे मेरे पास एक इंडेक्स वेरिएबल होती है इंडेक्स में करते हैं दो चीजें करते हैं की वैल्यू और पॉइंटर मतलब की वैल्यू जिसके बेसिस पे सर्च करना है जैसे हम सिंपल एग्जांपल लें आपके कॉलेज आपके पास एक इंडेक्स वेरिएबल होती है इंडेक्स में करते हैं में अगर आपके प्रोफेसर को आपकी डिटेल निकालनी हो ऑनलाइन ऑफलाइन की बात रजिस्टर करनी ऑनलाइन करके निकालनी हो आपकी यूनिवर्सिटी कॉलेज में तो क्या यूज करेगा वो की वैल्यू कौन सी यूज करेगा या आपका रोल नंबर या रजिस्ट्रेशन नंबर क्योंकि पता नहीं है उसके बेसिस पे सर्च करना इजी है तो एक की वैल्यू दूसरा पॉइंटर इंडेक्स का साइज ज्यादा करना है क्या होता है वो क्या इंडेक्स में आपको की वैल्यू मिलेगी टॉपिक का नाम और उसके कॉरस्पॉन्डिंग पॉइंटर पॉइंटर पेज नंबर फिर आप पेज पे जाके पूरे टॉपिक डिस्क्रिप्शन देख सकते हो जो कि सेकेंडरी में मतलब एक तरह से आपको विजुअलाइज करना है सीधे से बता सकते हैं अब जो इंडेक्स का साइज काफी बड़ा जाता है तो हम क्या करते हैं उसका भी मल्टी लेवल कन्वर्ट करते हैं इंडेक्स का आगे इंडेक्स बनाते हैं उसका आगे इंडेक्स बनाते हैं तो ये जो इतने लेवल्स बढ़ जाते हैं ना तो इनमें इंसर्ट करना और डिलीट करना मुश्किल होता है मतलब लेट्स से कोई एलिमेंट इंसर्ट किया सेकेंडरी में तो मुझे उसके कॉरस्पॉन्डिंग यहां सब चेंज करना पड़ेगा ऐसे डिलीट किया तो उसके कॉरस्पॉन्डिंग जो है उसको डिलीट करना पड़ेगा तो वो जो है डिफिकल्ट हो जाता है तो उस चीज को रिमूव करने के लिए उस चीज को बेटर करने के लिए हम यूज करते हैं प्लीज डेटा स्ट्रक्चर को और उसमें स्पेशल यूज करते हैं बैलेंस ट्री दैट इज बीटी तो बीटी जो है जल्दी यूज करते हैं मल्टी लेवल इंडेक्सिंग के लिए मतलब हमारा डेटा लेकिन हम इंडेक्स बनाएंगे यूजिंग द ट्री डेटा स्ट्रक्चर। अब ठीक है, आपको ऑलरेडी पता है कि ट्री के होते हैं, नोड्स होते हैं, एजेस होती है, जैसे सिंपल सिंपल दैट इज कॉल्ड रूट नोड। दीस आर ऑल योर इंटरमीडिएट नोड्स एंड दीस आर लीफ नोड। लीफ एंड इंटरमीडिएट, जो बीच में आते हैं दैट इज इंटरमीडिएट। लीफ को क्या कहते हो, और दैट इज रूट एलिमेंट। तो रूट के हम वैल्यू आते हैं एजेस के साथ कनेक्ट करके साइकिल के होता है, क्योंकि ग्राफ में साइकिल होता है लेकिन ट्री जो है वो ए साइकिल होता है। अब देखो यहां पे हम ट्री से अलग स्ट्रक्चर यूज करेंगे, ये बैलेंस है। बैलेंस का मतलब है कि सारे एलिमेंट्स जो है वो लीफ नोड के एक ही लेवल के होंगे, लेकिन यहां पे ऐसा होता है इस तरीके से बना सकते हो, क्या ये ट्री है, ये भी ट्री है, लेकिन यहां पे बैलेंस नहीं है, क्योंकि इसमें जो इसका आगे लीफ नोड यहाँ पे है, लेकिन इसके आगे कोई लीफ नोड नहीं है, तो दैट इज अनबैलेंस। क्योंकि ये जो लीफ है ये लेवल 1 पे और ये लेवल 2 पे बैलेंस नहीं है, लेकिन यहां पे मेजर करेंगे बैलेंस। अब जो भी बीटी की बात करेंगे इसमें सबसे पहले नॉर्मल मतलब क्या यूज करते हैं, एक यूज करते हैं ब्लॉक पॉइंटर या जिसको बोलते हैं ट्री पॉइंटर, जिसका काम क्या है, जो ट्री के हमारे पास यूज करते हैं, जैसे बात करें यहां पे ये मेरे पास एक नोड है। अब उस नोड में ट्री के नोड है जो नॉर्मल में ऐसे दिखाते हैं, लेकिन आप इस तरीके से बना सकते हो, क्योंकि नॉर्मल ट्री में एक ही बना देते हैं, इस नोड में बना दिया 10। यहां पे आपके पास ज्यादा वैल्यू यूज होती है, एक नोड में मल्टीपल वैल्यूज भी हो सकती है। तो देखो वो नोड आगे अपने चाइल्ड को जो है क्या कर रही है, डिनोट कर रही है। तो इसके लिए कौन सा पॉइंटर यूज करते हैं, ब्लॉक पॉइंटर या ट्री पॉइंटर, जैसे यहां पे यूज किया हुआ है। इस नोड के आगे लेफ्ट चिल्ड्रन है, तो ये कौन डिनोट करता है, ब्लॉक पॉइंटर या ट्री पॉइंटर। राइट चिल्ड्रन कौन डिनोट करता है, ब्लॉक पॉइंटर या ट्री पॉइंटर। दूसरा यहां पे बात करते हैं कीज। कीज का मतलब जैसे मैंने आपको पहले बताया कि किस बेसिस पे आपको सर्च करना है, तो वो सर्चिंग क्राइटेरिया क्या है, कीज डालेंगे। कीज हम इन नोड्स के अंदर डालेंगे, मतलब कीज आ सकते हैं, एक तो डाल सकते हैं, एक से ज्यादा कीज भी डाल सकते हैं, और उन कीज के कॉरस्पॉन्डिंग क्या होंगे, डेटा पॉइंटर्स या उसको कहते हो रिकॉर्ड पॉइंटर्स। वो उनका क्या यूज है, हर एक डेटा पॉइंटर, जैसे इस तरीके से मैं बोल रहा हूं और इस नोड में लेक्चर में डालना है। अब इनके कॉरस्पॉन्डिंग क्या होगा ना, एक रिकॉर्ड पॉइंटर होगा। वो रिकॉर्ड पॉइंटर क्या करता है, वो रिकॉर्ड पॉइंटर आपका सेकेंडरी मेमोरी में कहां पे पड़ी है, या तो सिर्फ 10 रखी, मतलब रोल नंबर है, लेकिन रोल नंबर के कॉरस्पॉन्डिंग नेम, फादर नेम, मदर नेम, एड्रेस, जेंडर, मार्क्स, मोबाइल नंबर, सारी इन्फॉर्मेशन पड़ी है, वो सेकेंडरी मेमोरी में पड़ी है। तो ये रिकॉर्ड पॉइंटर एक्चुअली उसको पॉइंट करता है। तो यहां पे सबसे पहला पॉइंट है कि कीज जितनी होंगी उतने ही आपके क्या होंगे, रिकॉर्ड पॉइंटर। ऑब्वियसली रखी मतलब रोल नंबर है, लेकिन रोल नंबर के कॉरस्पॉन्डिंग नेम, फादर नेम, मदर नेम, एड्रेस, जेंडर, मार्क्स, मोबाइल नंबर, सारी इन्फॉर्मेशन पड़ी है, वो सेकेंडरी मेमोरी में पड़ी है। तो ये रिकॉर्ड पॉइंटर एक्चुअली उसको पॉइंट करता है। तो यहां पे सबसे पहला पॉइंट है कि कीज जितनी होंगी उतने ही आपके क्या होंगे, रिकॉर्ड पॉइंटर। ऑब्वियसली हर एक की के अकॉर्डिंग एक रिकॉर्ड पॉइंटर किसको पॉइंट करेगा, सेकेंडरी मेमोरी में आपके एक्चुअल डेटा पॉइंट करेगा। इसलिए इसमें डायरेक्ट 20 तो 20 कॉरस्पॉन्डिंग रिकॉर्ड पॉइंटर जो है इस तरीके से पॉइंट करेगा। लेकिन अगर बात करें ब्लॉक पॉइंटर की, तो ब्लॉक पॉइंटर किसको पॉइंट करता है, ब्लॉक पॉइंटर करेगा कि नोड के आगे चिल्ड्रन कितने हैं, चिल्ड्रन जितने होंगे उतने ही आपके ब्लॉक पॉइंटर। इसी में साइड लेक्चर है। तो देखो कल जो स्टार्ट होती है आपकी ऑर्डर से, मतलब आपको इस तरीके से दिया होगा कि ऑर्डर ऑफ अ बीटी इज p, ऑर्डर ऑफ बीटी इज p। सो व्हाट इज ऑर्डर, ऑर्डर इज इक्वल टू मैक्सिमम नंबर ऑफ चिल्ड्रन, मैक्सिमम नंबर ऑफ चिल्ड्रन आर नोन कैन हैव, मैक्सिमम नंबर ऑफ चिल्ड्रन आर नोन कैन हैव, दैट इज फॉर योर ऑर्डर। तो देखो अगर हमारे पास लेट्स से ऑर्डर दिया हुआ है 4, लेट्स से ऑर्डर हमारे पास दिया हुआ है 4, तो इसके क्वेश्चन आप क्या कर सकते हो, अगर ऑर्डर 4 है तो आप यहां पे ये टेबल याद रखना कि जो रूट होगा, रूट में मैक्सिमम चिल्ड्रन क्या होगा, चिल्ड्रन जो होगा कि मैक्सिमम चिल्ड्रन कितने होंगे, रूट में मैक्सिमम चिल्ड्रन कितने होते हैं p, और मिनिमम चिल्ड्रन रूट कितने होंगे 2। इंटरमीडिएट नोड मतलब चाहे बीच नोड चाहे लीफ नोड, तो उसके जो मैक्सिमम चिल्ड्रन कितने होते हैं p और मिनिमम चिल्ड्रन कितने होते हैं p by 2 की सेम वैल्यू। तो ये याद रखना, इंटरमीडिएट नोड है उसके मैक्सिमम मिनिमम चिल्ड्रन कितने होते हैं, और जो रूट नोड है उसका p और 2। अगर आपको यहां पे वैल्यू दी हो लेट्स से 4, ये मतलब वैल्यू आपको दी है कि ऑर्डर ऑफ बीटी इज 4, तो अगर ऑर्डर ऑफ बीटी इज 4 तो मैक्सिमम नंबर ऑफ चिल्ड्रन कितना, मैक्सिमम नंबर ऑफ चिल्ड्रन होंगे, तो मैक्सिमम नंबर ऑफ चिल्ड्रन आपके होंगे p, दैट इज योर रूट। तो मैक्सिमम चिल्ड्रन कितने होते हैं 4 और मिनिमम चिल्ड्रन कितने होते हैं 2। तो अगर मैक्सिमम चिल्ड्रन आपके 4 कितने होते हैं, इस तरीके से बना सकते हो। जैसे ये देखो ये आपका ये चिल्ड्रन 1 गया, ये चिल्ड्रन 2, ये चिल्ड्रन 3, ये चिल्ड्रन 4, मैक्सिमम चिल्ड्रन कितने होते हैं 4।